This is the first of two parts covering Light and Sound in Experiment 11 of Make Electronics by Charles Platt, 2nd edition. Today we'll be concentrating on this upper box, part of a two-part circuit that's making the noise. In part B, we'll deal with that bottom part. Let's look at the parts we need. It's a big, complicated build, so it takes some time getting everything together. Make sure that your NPN bipolar junction transistor is in fact the 2N2222. Make sure you got the right part number. In addition, we'll need a generic LED, a whole bunch of resistors. Make sure you go through the list we need and get them sorted out. Identify your loudspeaker. Make sure you strip the ends of the loudspeaker if you haven't already. And then we need a whole bunch of capacitors as well, both ceramic disc capacitors. Make sure that you have the 0.01 microfarad and separated from the 0.1 microfarad. Now the 0.1s may have just a label on them. In this case, it's a 104M is what's written on the capacitors. There'll be a different code for different ones. And in fact, the 0.33 microfarad capacitors may have no label at all. They may just be a small blue capacitor. The electrolytics, which come in the cylindrical cans, have a polarity. They're used for larger values, and it's important that you hook them up the right way. So again, today we'll be building the top half of that buzzing circuit. Next time we'll be doing the audio part and having you customize it to make your own sounds. But for today we're going to concentrate on the basic physics behind how an oscillator works. Now let's take a quick look at how I've built this circuit. I've been careful to use cut jumper cables so I can troubleshoot. I am using resistors without cutting them down quite yet. That's important if you can, but make sure the leads don't touch each other, right? So you have to make sure that each resistor or capacitor goes into the hole it's supposed to go into without touching each other on top or warbling back and forth. Now that's not the best idea, but it's very important because we're going to be soldering the circuit in the next chapter. All right. Let's look at how this oscillator works. So this is going to be a four-step process. We'll break it down into just two chunks at first. In the first one, we said that the left capacitor is filled up. Meanwhile, the right capacitor is charging. That means that current is going on the opposite side of the right capacitor and going into the base of the right transistor, which turns that transistor on and allows current to flow on the right side of the circuit. Now steps 2 and 3 will combine for the moment. And you can see the opposite is happening. The right capacitor now is filled up and the left transistor is on. Meanwhile, the left capacitor is charging and the right transistor remains off. Now step 4 looks a lot like step 1. And things have reversed because the left capacitor has now fully charged, it's completely full, the right transistor is on, and then the right capacitor is starting to charge, leaving the left transistor off. Let's look at it one more time. Okay, steps 2 and 3, the right capacitor is full, the left transistor is on. Take a moment and be sure that you understand the mechanism here. If you have the current flowing into the capacitor side of a circuit, it's not available to flow into the transistor. The transistor will only get energized when the base draws current. That only happens when the capacitor it's attached to is acting as if it's open, that is, it's completely full and not charging. Steps 4, again the process reverses and it loops back to the beginning to step 1. I'm going to break it down now into some detailed steps. Notice that red color in the simulation, it's a white line that's drawn in the textbook figure that indicates a sudden change on the left capacitor. That's the displacement current from last time. That sudden change in currents go right through the capacitors if it's a short. That drags down the current on the base very quickly, completely shutting it off. That happens in both step 2 and step 4 on the other side of the circuit. So you get a rapid change in displacement current, pulling the base down, turning it out rapidly. Now on steps 1 and 3, the right capacitor is charging very slowly, and that's because the resistor on the charging side, 470K, is much bigger than 4.7K. The next part of the circuit, or I should say the full part of the circuit for flashing the LED, is shown here. Author suggests you add a 100K resistor that is on the left side of the circuit above the transistor, and that powers a third transistor. That third transistor then has a 1K current limiter. The idea here is that when the left transistor is on, that has very low resistance, so no current flows through that large 100K resistor. When the left transistor is off, it has high resistance, and therefore current does flow through that resistor. Let's view this in the oscilloscopes. You click on the right mouse button on, say, that 1K current limiting resistor. It should bring up an oscilloscope trace, and then you can click on one of the traces. You'll see there's both a current and a voltage trace. Let's turn the current one off, so now we only see the voltages. And it's kind of what we expect, a really sharp turn on and turn off. Let's investigate the time constants numerically. So first of all, the time that the LED is on is going to be given by R times C, where R is now the charging time of a capacitor, 470 kiloohms, and the 0.33 microfarad. Now, in the textbook, they used a larger capacitor, 3.3 microfarad instead of 0.33. I sped mine up for both the simulation and the video to make things go a bit quicker. So I get a time constant of 0.16 seconds, whereas the book gets 1.6 seconds. And that's what you would build if you follow the textbook exactly, as a 1.5 second on and an off. Now, the time the LED off is the same as the mirror circuit, but the rise time is a lot faster. The final step today is to insert an additional capacitor. That's the 220 microfarad that is across the LED and bottom 470 ohm resistor. This makes the transient time much, much longer. So 470 ohms times 220 microfarads is 0.1 seconds. That's almost as long as the 0.16 seconds in my circuit. And that means that the LED never goes fully on or fully off. Instead, it's now just going to pulsate or slowly go up and down. And I can change that time constant by changing the value of the resistor. If I make it 22 microfarads, I see I get a bit of a slower rise and slower fall, but I still have sort of a pulse-like behavior. And if I make the capacitor quite small, I will see that I will recover the original behavior as if there was no capacitor. That's because the time constant of 470 ohms times the capacitor I'm adding gives a time constant that is extremely short. So go back to flashing behavior of the LED, and it's nice the simulation actually shows the LED growing brighter or dimmer or flashing on and off. Let's go take a look at how this circuit is actually built. We're going to show you the modifications you do to put this smoothing capacitor in at the output of the circuit. And this is just a great technique to know because it allows you to modify circuits and change their shape. Those of you who have done a bit of audio know there's a huge difference, say, between the way a square wave with the rapid transient sounds versus the sawtooth wave I've shown you here. And this is one way you can change one into the other, is by using that coupling capacitor. Okay, back to the breadboard. We're going to make that modification where we remove the 1 kilo ohm and resistor that goes right into the LED, replace it with two 470 ohm resistors. Now 470 plus 470 is about 1,000 ohms, so we've kept the resistance in the circuit about the same. The first 470 ohm resistor is going to limit the current going into the LED, as will the second, but the second has another role to play as well, which is that in conjunction with that capacitor, it's going to give us a time constant, the one that I just showed the effect of in the simulation, to slow down the charging. So you have to do a little bit of creative breadboarding here. The book suggests one configuration. You can do some others, but the bottom line is you got to pull the 1K resistor and replace it with two 470 ohm resistors in series. The second resistor and the LED you bridge across with the capacitor. And let's see how that looks. Here we see the LED flashing, and we're ready to grab one of the electrolytic capacitors. You can make sure the polarity is correct with the long leg towards the negative side of the circuit. And the flashing should go from abrupt to sort of a pulsating glow, slowly turning on and off. Check it a few times. Let's go pull it out temporarily. remove that capacitor. There's our square wave with sharp transitions. And there's our sawtooth wave, slowly going up and down. Your pulsating effect may be slightly different if, as the textbook suggests, you use the 3.3 microfarad instead of the 0.33 blue ones as I did. Okay, here's the Experiment 11A assignment, a stepping stone towards building the full little music synthesizer that I showed at the beginning. So please do build the circuit in figure 2.1.16. Demonstrate a pulsating LED and place a very brief video, please only just a few seconds long, in your logbook of it working. Now I'd like you to experiment with all the different resistors and capacitors in that circuit. So go in and swap them out, not just on both sides of the circuit at the same time, but on the left versus the right. Use slightly larger values for each resistor. So say replace a 4.7K with a 10K or even 100K. And then with the capacitors, replace them with both larger and smaller values. I don't want you to do much smaller values on a resistor because we don't want you to accidentally short anything out. Make a table that explains the function of each component in the circuit that you understand from the simulation, the book, this video lecture, and primarily just with playing with it. Label your table using the annotations which are given in figure 212. So little r1, big R1, little r2, big R2, Q1 and Q2. Again, Q is a symbol that for historical reasons is typically used for transistors. Please explain the function of the 100K resistor and the two 470 ohm resistors as well. And then finally, please write up a summary about what the differences are in the behavior between those two 470 ohm resistors. Keep your circuits together. We'll be adding on the bottom part in the next lecture.